In this video, we're continuing to think about continuous annuity problems from Kellison's book on the theory of interest, problem 4.49. We're going to be finding a few different formulas for the present value of a decreasing continuous annuity. It's a special decreasing continuous annuity, a standard one. Here's the problem statement, two parts to it, part A and B. In part A, we're going to be finding an expression involving an integral for this present value right there. What is this present value? It's evidently, well, first of all, it is a present value because you see an A. It's continuous because you see bars above the D and the A. It's decreasing. It occurs over a period of n years, if time is in years, or it could be n months if time is in months. Part B will be dealing with the exact same thing, but an expression not involving integrals. All right, and we'll sort of do parts A and B all together. H of t, the cash flow in this situation, is taken to be the special function n minus t. So that would be a linearly decreasing function with a slope of -1 and a vertical intercept of n. So initially at time 0, money is flowing into your account at a rate of n units of money per unit time. But over time, and when you get to time n, this goes down to 0, and no money is flowing after that point. The assumed discount factor here is the accumulation function to the -1 power is going to be e to the negative delta times t. We're assuming a constant force of interest when we use these symbols here. So as I've discussed before, to find this present value, which again, let's write the symbols down, d bar a bar sub n, we need to integrate the product of h of t and the discount factor here. That's going to give us the integral of n minus t e to the negative delta t as t goes from 0 to n. And I guess you could say this answers part A. It's one way to answer part A at least. There's an expression involving an integral for this present value. I'm now going to do integration by parts to try to evaluate this integral. And in doing so, you should recall in doing integration by parts, you get another integral that is hopefully simpler to do. I suppose you could consider this other expression that we're going to derive yet another expression for this present value. So with integration by parts, let's keep the limits of integration as they are here, 0 to n. Let's let u equal n minus t, so that du is negative dt. And let's let dv be e to the negative delta t dt, so that v is -1 over delta e to the negative delta t. This would be the good integration by parts to do. I will keep the limits of integration as they are, as I should with integration by parts. You would only change the limits of integration if you were doing a substitution, but that's not what we're doing. We're doing integration by parts. We've got u times v is going to give negative n minus t over delta e to the negative delta t as t goes from 0 to n. And then minus the integral of v du. There are going to be 3 minus signs here, that one, and that one. So we'll still have a minus sign. We'll also bring the 1 over delta out in front. And we get this. This is another expression involving an integral. Let's keep this integral the same and simplify this part. Careful with these minus signs here. If we plug in t equals n, we get 0. And then we subtract what we get when we plug in t equals 0. E to the 0 is 1. N minus 0 is n. Have a minus sign there. You're going to end up with n over delta. That's what that simplifies to. So yeah, you could say what I'm writing right now is another expression involving an integral for this present value. So you could say perhaps that this is the answer to part A as well. How about an expression not involving integrals? Well, there are a few different options here as well. This integral has a symbol. It's a bar sub n. It's the present value of a level or constant continuous annuity where the money is coming at a rate of 1 unit of money per unit time. So yet another formula for this. An answer to part B that doesn't involve an integral. If you simplify, you could write it as n minus an over delta. That can be an answer to part B. There are other possibilities. This equals n minus, what's the formula? Oops, I forgot my bar here. What's the formula for a n bar? It's 1 minus v to the n over delta. Or v to the n can also be written as e to the negative delta n. Okay, so various kinds of formulas. You can also subtract the fractions on top by getting a common denominator. You can write delta times n minus 1 plus v to the n over delta on top, and then we also have a delta on the bottom, so we get a delta squared. Again, this is e to the negative delta n. That could be written that way. Various ways to write this. Any of these, conceivably, based on how the problem is stated, it could be thought of as being an answer. Let me finish this video by doing something I usually don't do. Now let's think about the graph of this thing. Let's go ahead and consider this last expression with the e in there. Delta n minus 1 plus e to the negative delta times n over delta squared. I took the chance of graphing this as a function of delta for fixed n, just to see what it looked like. So delta is going to be the horizontal axis here, and the vertical axis is going to be this present value, d bar a bar sub n. And what I found was, when I graphed it with my technology, that the graph looked like this. It was a decreasing and concave up function of delta. And, well, it's not defined at delta equals 0, but it does have a limiting value as delta approaches 0. The limit as delta approaches 0 from the right of this expression right here turned out to equal, could we guess what it would equal? Well, you could pause the video and try guessing yourself, or you could try to figure it out. If you were going to really try to guess without just thinking about the formula, how would you guess? Well, delta going to 0 means the force of interest is going to 0, which also means the interest rate itself is going to 0. And in the situation where there's no interest, when the interest rate is 0 or where delta is 0, the time value of money doesn't come into play. Money has the same value no matter what the time is. And so the present value of a cash flow like this would just be the actual value of the cash flow, the nominal value of the cash flow. In other words, it would be the area under this graph. We don't have to discount anything. The area under that graph, it's a triangle, is 1/2 base times height is 1/2 n squared. You could also use calculus to calculate that. And that is what this limit ends up being. You can check that this limit ends up being n squared over 2. Okay? Maybe kind of surprising, kind of cool. It does equal the area of this. It equals the nominal total value of the money you get from your cash flow, so you're not taking the time value and money into account. And that should make sense then. Let me add on a little bit more to that by saying there's another way you can verify that this limit is n squared over 2. That you can use L'Hopital's rule. The limit of this as delta goes to 0 from the right. It is a 0 over 0 indeterminate form. If you plug in delta equals 0, on the bottom you definitely get 0. On the top you get 0 minus 1 plus 1. E to the 0 is 1. You get 0. So if we apply L'Hopital's rule and differentiate with respect to delta, here's what we get initially when we differentiate with respect to delta, not n, with respect to delta. This is also a 0 over 0 situation. Bottom's definitely 0 when delta is 0. The top is n minus n, or 0 when delta is 0. Use L'Hopital's rule again. This equals the limit as delta goes from 0 to the right. Differentiate with respect to delta. You're going to get a positive n squared e to the negative delta n over 2. And as delta goes to 0, that goes to n squared over 2. So that's nice to see that you do indeed get the same answer with L'Hopital's rule as the graph gave us.